Okay. Hello, everybody. Welcome to the last day of our conference here in Wrocław. It's still great to see so many faces. And we start our morning session today with Tim, who is actually telling us about a new perspective on non-commutative deformation of field and gauge theories. Please, Tim.
Well, I hope you can hear me. Yeah, so thanks for the introduction. Also, thanks to the organizers for organizing this nice event and inviting me to speak. I will talk about non-commutative field theories, especially gauge theories, and in principle, how we introduce a new perspective on how to define and construct those theories. So let me first start with giving you a brief motivation why we are interested in non-commutative field theories in the first place. And for me, they appear in deformations of this ADS CFT correspondence. So in its most famous example, take ADS 5 crosses 5 string. It's dual to n equals 4 super Young Mills. And just to recap, like both of these models, they share the same kind of symmetries generated by this PSU 2,2/4 algebra. And then you can do various things with them. For example, in the planar limit, you find on this side, you find string sigma models. You can construct Lax pairs. So you have integrability. And on the string theory side, this gives you some control on the string spectrum. While on the field theory side, integrability appears in as spin chains and their spectrum for the anomalous dimension of gauge invariant operators. So you can see them in the 2-point functions. Well, this is a nice setup, but in recent years, people started studying whether you can extend these ideas to further models. For example, by deforming these models in a particular way. While preserving integrability. And one particular class of such deformations of the string theory side is given by Young-Baxter deformations. And here you take a so-called solution to the classical Young-Baxter equation. And during this talk, like I will just talk about things that are related to solutions to the homogeneous classical Young-Baxter equation. So you take such an R matrix and you deform the string in a certain way. And the resulting theory then lives on a deformed ADS space and admits a twisted version of this PSU 2,2/4 symmetry. And then you can ask several questions. For example, can we do something similar on the field theory side? Can we deform the n equals 4 super Young Mills in such a way that we arrive at potential dual candidates to these ADS strings? And the idea is relatively clear. Since there's this twisted version of PSU 2,2/4 appearing here, we should kind of deform the symmetries in the same way by using the same kind of twist. And then we arrive at this corner down here, some deformed version of n equals 4, and we can start asking questions about its properties. How do observables look like? Do we still have integrability? And by answering these questions, we then could also shed light on this question mark here, whether these theories are really corresponding to each other. Well, it has been conjectured that this corner down here is given by non-commutative field theories, non-commutative deformations of n equals 4 super Young Mills. And this is what I will talk about today. I will talk about this process here, how we take n equals 4 or gauge theories in general and deform it by using its symmetries to get non-commutative versions of it. Okay. So this is my outline. I will first introduce the basic object, Drinfeld twists, and how they change symmetries so that you can understand what we are actually doing. And then I will jump in to actually derive these non-commutative field theories as deformations of their undeformed theories. And here I will compare, in principle, two pictures how we can view this twist to act on fields. The first one is more the conventional picture, which we call the Lie derivative picture. And the second will be more driven by actually using the fact that we are dealing with symmetries. So we will let the twist then act as active symmetries on our fields. So this is why we'll call this the active picture. In the last part of the talk, I will start talking about Feynman diagrams as the first properties that we are looking at in these theories, and then I will conclude in the end. Okay, Drinfeld twists. So in order to understand what a Drinfeld twist is, we first have to think about symmetries and formalize them in the right language. So take, for example, translation generators. They are basically partial derivatives, and they act on fields, and in particular, they are pointwise products of fields via the usual Leibniz rule. And this is, in principle, what we are going to deform, and we do this by first formalize this in terms of the right language, and this is using coproducts and Hopf algebra structures. So we basically introduce this mu, which is a map acting on the tensor product between two fields, and is giving, it's basically just encoding this pointwise product. And then if we take an element x of some algebra of symmetries and we act on this pointwise product here, then this is given as first acting with this delta of x on this pointwise product. And this is just the coproduct with respect to this element x. And then afterwards taking the pointwise product of the result. This here, you mean? This is an index, and yeah, this is just the index. It has nothing to do with it. Yeah, very good. Right. And this coproduct is then what basically encodes this Leibniz rule. So this is how it looks like. And if you work it out, it exactly gives you back this Leibniz rule. So we can now introduce a Drinfeld twist, which is an object that lives in the universal enveloping algebra of this G tensor itself. And this will now define as a deformed or twisted coproduct, which we call delta F. And this is the composition of the twist itself, the ordinary coproduct here, and this inverse twist. Yeah, so this defines some notion of new product rule when we act on fields. And we now want to have an algebra of fields that respects this new product rule and the new coproduct. So what we do is we introduce a twisted product on the functions, on the fields here, called mu f. And this is the composition of this old pointwise product that already appeared here, and the inverse twist that first acts on this tensor product between fields. And then you can work out that, in principle, now acting with x, again in this algebra, on this twisted product between fields is exactly satisfying a similar product rule as here, but now with this twisted coproduct. And we now want to take all undeformed theories and, in principle, replace products in such a way that by this twisted product, so that it has a natural notion, a natural product rule with this twisted coproduct instead of the old one.
Basic question. When F is living in this tensor product, what do you mean by F inverse?
So, I mean, we have this F, and like to be a Drinfeld twist, it has to satisfy some identities that I will not go into detail, but one of them is that it's invertible. So you literally take the twist, you act on two fields, and you then act with the inverse, and then it basically gives you the identity. So yeah, F times F inverse is the identity tensor, the identity, basically. Okay. So this mu f will be the central product that will appear later on, and we just call this a star product, and we just write f star g. This is non-commutative, so it's not the same as g star f, but because it's built from a Drinfeld twist, it will remain associative. We can, as this will appear everywhere, like we just repeat this process for all kind of fields and all kind of objects that will appear in our theory. So for example, we can construct, or we can define star products between vector fields, and also the wedge product between forms in principle will be replaced by the star wedge product. And they are all having the same kind of structure. So we act with some certain way with this inverse twist on these objects, and then we take the undeformed products of the result. Okay, so this is relatively abstract. So let me actually give you some examples of twists so that you might get a better imagination of what these things actually are. So the first example that I would like to show you is this twist built basically as this exponential of essentially the tensor product between internal charges. And in the context of n equals 4 super Young-Mills, this is what will lead, this particular twist leads to the so-called beta deformation. It's a marginal deformation. And since this twist is only built purely from internal symmetries, there's no deformation of the space-time, but it still has a non-trivial star product. The star product between two fields is then given as the normal product, but dressed with a phase basically that depends on the charges that are measured by these charges here when acting on the two fields. We can also do consider twists that are built with space-time symmetry generators. So for example, we can, in the twist before, we can replace one of these charges by a Lorentz generator. And the result is then what we call the angular dipole deformation. So the effect of the star product here is that you shift the angular dependence of the individual fields by something that is proportional to the charge that is measured by this Q when acting on the other field. And you can do other kind of dipole deformations, for example, using, like in principle, using the dilatation operator here. And then instead of shifting the angular coordinates, you rescale the coordinate dependence of the fields by something that depends on the charges. Of course, the next step is to just replace all internal symmetries by space-time symmetries. So, for example, if we build a twist purely from translation generators, then this is what leads to the famous Grunewald-Moyal deformation. And the feature of this twist is that it already admits a non-trivial star product when acting on coordinates. So this leads to this star commutator between coordinates that is actually non-vanishing. In this case, it's relatively simple. It's constant and proportional to this deformation parameter theta. But the feature is it's non-vanishing. And this is why we call the resulting spaces non-commutative. We can do more involving things. For example, in this Lorentz deformation, we consider a twist built from Lorentz generators, and then this non-commutativity becomes more involving and actually non-constant in this case. So we can also do more things, like these all have been examples of abelian twists, but we can also do, in principle, could consider more complicated algebraic structures of twists, or also try to look at twists where we have supersymmetry generators also appearing. So in principle, algebraically, these could also all be things that we would care about. And in principle, but the story is similar. Like we always introduce the star product, and this does something with our spacetime, and we want to construct gauge theories or field theories and gauge theories on these spaces. And this is the next step that I want to discuss, how we actually do this step, how we define gauge theories on these non-commutative spaces. And the idea is in principle relatively simple. We want to replace all the products that appear in a given undeformed theory by this twisted star product. And the more conventional picture is then, like, first I have to tell you how the twist actually acts on fields. And the more conventional picture is that you take this twist and also this universal enveloping algebra of G, of the algebra of symmetries, to act as Lie derivatives on your fields. So there have been various papers basically using this approach for various twists and various examples. The problem is that when you are talking about gauge theories, you want to make the theory gauge invariant. And this is actually quite hard to achieve. And for just a general twist, the most you could hope so far is to make gauge invariance just appear perturbatively in the deformation parameter. But for some examples, you actually can go further, and you can actually write an action that is gauge invariant in all orders of the deformation parameter. For example, during my PhD, I worked on the examples in the Poincaré algebra, and we derived a procedure there which you can use. We further generalized this to also include conformal, to also include the dilatation generator in the twist in cases where the undeformed theory to start with is at least classically conformal. So in this Lie derivative picture, you have a natural action of the twist on all the fields that can appear, because it's just Lie derivatives. So in principle, this picture is also even independent from deforming by symmetries, because you can just take any vector field, you can build the twist, and in principle, you have a notion of how this twist acts on your fields. But the problem is always defining gauge invariant theories. And the reason for this is that we have to work with differential forms, as we will see in a second. And when we are talking about Yang-Mills theory, a formulation like this automatically includes Hodge duals and Hodge operators. And these actually cause problems with gauge invariance. So let's dive into this and why this is happening. So the first thing you want to do in a gauge theory is to construct covariant derivatives and the gauge field. And let's start with an adjoint scalar field. And we just follow these first principles that we have. We want to replace products by star products. So also the gauge transformations of this object will involve a star commutator instead of a normal commutator. The problem, however, is when we now want to construct covariant derivatives, we want to look at how partial derivatives of these fields transform. The problem is partial derivatives, they don't obey the usual Leibniz rule, so they don't have the nice structure that we have in the undeformed case. Instead, we can look at exterior derivatives, and they just by construction commute with Lie derivatives, so they will commute with a twist and hence with a star product. So the exterior derivative of this field phi then transforms as the sum of these two terms. We can now introduce a gauge 1 form that basically, when defining a covariant exterior derivative, cancels this first unwanted term in the gauge transformation, so that this object here will transform covariantly, star covariantly. Right, and then we can start defining a field strength tensor. This also transforms nicely star covariantly, but the problem is then when we are talking about Yang-Mills, we have to look at the Hodge dual. And the Hodge dual in general is not, or the Hodge operator is not star linear. So when we take the Hodge of a function f, star multiplied with, for example, this field strength tensor, this is not the same as doing the operations the other way around. First, considering the Hodge dual of G, and then star multiplying by f. And for the gauge transformation, this means that this object doesn't transform nicely. And when we build actions using these objects, they will not be gauge invariant. So that's something that automatically happens for general twists in this Lie derivative picture.
Certain twists you were able to construct. There's like a special case as well.
Exactly. So yeah, so this statement here becomes simpler. So actually, the Hodge dual remains star commutative, star linear for cases where the twist is built from Poincare algebras, essentially. Right. So, but this is the reason why we changed the picture, and we literally use the fact that we are like our motivation comes from twisting a theory by using its symmetries. So we let the twist, instead of acting as Lie derivative, we let the twist act as active field transformations. So they have such a structure. So we change the field, and it's given by, well, some transformation here. And active transformations during this talk, I will always note by hatted objects, so to distinguish them from the Lie derivative picture. And in principle, these active transformations, they transform into these fields into each other, where this object here is a matrix, but can also contain differential operators, for example, like it would be the case for space-time symmetries. So, right. Then in principle, I can use a twist that now acts via active transformation on all my fields, and I can define an associative star product using this. I will just call it the hatted star product. It's associative, again, because the twist is a Drinfeld twist. And this product here is also, or the algebra of fields with this hatted star product, again, forms a representation of my twisted Hopf algebra. So it's exactly that what I want. And then we can see some advantages of this approach over the Lie derivative approach. For example, since these fields, they have a direct action, since active transformations have a direct action on the fields, the star product automatically commutes with partial derivatives. And since this is the case, we don't have to use differential forms. We can directly work in component fields, and we don't have to use the Hodge operator, which caused problems. There are some disadvantages per se, because when we are talking about active field transformations, the undeformed theory should better be invariant under the transformations that we have. Otherwise, talking about active transformations doesn't make so much sense. But this is not really a problem, because given our motivation, we are interested in deforming our theory by using the symmetries anyway. So we are fine with that. Okay, let's talk about Leibniz rules for partial derivatives. So as I said, active transformations by construction, they commute with derivatives because they directly act on the fundamental fields. And that means that the partial derivatives commute with the headed star product and hence satisfy the normal Leibniz rule even with the headed star product. And this allows us to work directly in component fields. So let's repeat this thing of constructing covariant derivatives, but now on this active picture. So what we immediately see is that this object here transforms as the sum of these two terms. And now we can literally, like in the undeformed case, just introduce a gauge field that transforms appropriately in order to cancel this first unwanted term when we define a covariant derivative. So that's nice. And we can immediately go further and can construct a field strength tensor, which looks like in the undeformed case, but again, just products replaced by this headed star product. And this also transforms covariantly or star covariantly. And then with this, we can start building an action. And this action, again, like just replacing products by star products, will transform as the integral and the trace over the star commutator. So if this would be a normal commutator, the trace would kill it because it's antisymmetric and the trace is cyclic. The problem here is that we have star products and they are non-commutative. So this will not be the case in general anymore. So this term for general twist is not vanishing. Okay? But we can restrict the twists to classes where it does vanish, because we can restrict the twist to give us a star product that is actually cyclic when we integrate over space-time. And yeah, that's just a condition that we impose on the twist. So let's see what are the implications of this on the twist. So we want to compare these two things. Like when we multiply two fields with each other, then cyclicity is relatively simple. So we want to compare G head star H with H headed star G under integration. So let's start with this first term, and we can rewrite the star product using the twist explicitly. This is what we get. And now we can use a notion of partial integration in principle to bring this F with an upper index alpha to act on G instead of H. By doing this, we have to introduce this antipode, which is a structure in Hopf algebras, basically turning elements to its negative. This is also why you can see this as partial integration. And this is true up to total derivatives. So this object here together, we just give it another name and we call it V. And now we play the same game again. We take this equation here and we just partially integrate so that V now acts on H, but with an antipode. And now we can start from this object here and we can repeat this first three steps, but now H and G are exchanged, so we have V acting on H instead of on G. If those terms agree, then we have to demand that we are dealing with twists where this V is equal to its antipode. So this is the condition for cyclicity that we get. And this is what we can call weak cyclicity, because actually in the literature, there's a stronger version of this where this V that appears here is set straight to 1. So these are, we figured out that this is a condition that is a little bit too strong and that excludes some twists that we want to deal with. For example, it would straight away exclude some unimodularly extended Jordanian twists in the right picture that we want to deal with. So what happens when we don't do this is that we have to deal with these star products, and they also will appear in quadratic actions. So what happens is that we have deformed quadratic actions, which leads to deformed propagators. If instead we would set this to 1, we have the fact that in a sequence of star products under integration, we can always remove exactly one star product. In a quadratic action, that would lead to undeformed propagators. So this is the difference between these things. Okay, let me recap and summarize in principle this active picture here. So we view our generators that appear in the twist as active transformations. So we demand them, or they have form of that kind. And this form is actually obtained for various kinds of symmetries. So we can deal with internal symmetries. Here, this psi would be a matrix. We can deal with space-time symmetries. There, this psi appearing here is more differential operator. And also in the right, in the right formulation, we can also deal with certain supersymmetries. Well, we have to have, in order for this to work, we need off-shell representation of supersymmetry on our field. So we definitely need all various kinds of auxiliary fields when we want to deal with supersymmetry. So this is a caveat that we have. But otherwise, it's fine, and we can deal with this with supersymmetries in the definition of our twists as well. The other condition, this weak cyclicity condition, actually reflects on a condition on the classical R matrix that, if you remember, appeared on the Young-Baxter deformation side as well. So it is actually necessary for this weak cyclicity condition that the R matrix is unimodular. And this unimodularity condition on the Young-Baxter side appears as a condition for giving a good supergravity background and giving wide-invariant theories. So there seemed to be some link between demanding cyclicity of the star product and this property here of some kind. Okay, so that's basically the setup and how we can deal with with these twists and how to define non-commutative versions of gauge theories. So let's start to look at the first things that you could care about in those theories. In the end, we are interested in computing correlation functions because we want to see integrable structures and so on. So the first thing to look at would be Feynman integrals and Feynman rules. So as I said, when we demand the weak cyclicity condition, we have deformed propagators, and in fact, they are just deformed by having this object V that appeared in the cyclicity condition just acting on the undeformed propagators. This is how they look like, and for vertices, we have this rule that we have these star products appearing to act on all these kind of vertices because we have star products appearing in the interaction terms, of course. If we were to demand strong cyclicity condition, these things, they simplify a bit because this V that appeared here is just straight 1, so the propagators are undeformed. But we still have star products that appear at the vertices. However, we can remove exactly one star product in these vertices. So that helps a lot for building Feynman diagrams. So take, for example, such a planar diagram here. It's a relatively simple one, but we can see what's happening very, very nicely with this one. So in the strong cyclicity, with having the strong cyclicity condition, we can remove exactly one star product at both of these vertices, which leads to this diagram here. And then we have two star products acting on the same propagators, but in different orientations in the end, which will make them cancel. So that this diagram, this deformed diagram with all these star products, is given by its undeformed counterpart up to twists or star products only acting at external positions. And this actually we showed already some time ago for all these strong cyclicity twists is true for all kind of planar diagrams that you can build. But the remarkable thing is that we can even generalize this to twists that only have the weak cyclicity condition. We have, I mean, everything looks more horrible. We have deformed propagators, and we also cannot remove one star product from the vertices, but somehow things align such nicely that in the end we have the same property. We just have undeformed Feynman diagrams up to star products or twists only acting on external positions. Yeah, so that simplifies a lot how we have to deal with Feynman diagrams and will simplify the next step in the future to compute two-point functions and correlation functions in general in these theories. Okay, that already brings me to my conclusion. That already brings me to my conclusion. I showed you how we introduced this alternative active picture to construct non-commutative gauge theories. This approach is driven by using the symmetries of the undeformed theory. Yeah, and we can construct gauge invariant actions for theories that are literally deformed by using its symmetries. But this setup is relatively general, and we can definitely include all kinds of internal symmetries, space-time symmetries, and to some extent also supersymmetry generators in the construction of our twist. So in principle, we have everything together to use the full PSU 2,2/4 symmetry of n equals 4. We also relaxed this cyclicity condition to this weak cyclicity condition, which is which even improves the class of twists that we can deal with even more. And then I've shown to you that for planar diagrams, we have this planar equivalence theorem that relates every deformed planar diagram to its undeformed up to twists only acting on external positions. Okay, so what comes next? Since we now constructed all these theories, we would go to the next step towards finding integrable structures in the deformed versions of n equals 4 super Yang-Mills. So we want to construct and calculate, for example, two-point functions of gauge invariant operators for all these kinds of various twists. Here we hope to find twisted beta equations and integrable structures. Yeah, and there are some papers that already give hints that that this is actually true. So, for example, some people studied dipole-like deformations where they found spin chain integrability, and also in the case of the beta deformation, even longer ago, this has been found. So another direction that is very interesting is to directly complete the construction of these kind of models directly in the Lie derivative picture. And here I would like to refer to the poster of Julio, who those of you who didn't have the chance on Tuesday to talk to him, he's still here. So if you are interested, go find him and talk to him. Beyond these stories of twist deformations, it would also be interesting to extend this kind of constructions to models dual to the inhomogeneous Yang-Baxter deformations. The problem with those is that the symmetries are not given as a twist of the PSU 2,2/4, but a proper Q deformation. And this is something that so far we cannot tackle with this approach, but it would be nice to go into that direction, of course. And then something I got into more recently is to try to construct MHV-like amplitudes and like all these kind of constructions for these deformed versions of n equals 4 super Yang-Mills. And here it's quite helpful that we also extended the ideas that we have in these space-time theories also on twistor space. So we can define non-commutative twistor space and gauge theories thereon. And this would be a good way to also look at amplitudes in deformed versions of n equals 4. Okay, thanks.
Okay, thank you very much for this nice talk, Tim. So we have some time for questions actually. Are there questions?
So thanks for the nice talk. So maybe, I don't know, maybe it's a naive question, maybe I misunderstood something, but to me it seems that you are essentially discriminating like good twists from bad twists based on like properties of the start products that you are considering in your field theory. But isn't that like too restrictive? Because you know that you can, in some sense, you can perform like nonlinear changes of bases of this quantum universal enveloping algebra, and therefore like find other realization, right, of this algebra in which the start product in principle might exhibit like different kind of features, right?
That's a good point. But I mean, just for context, it's true that these star products, they are defined up to field redefinition. So you can do a field redefinition to change a twist into what is called an equivalent twist. And they in principle look different and they can have different properties. But there's one thing that you cannot change. And this is, for example, the unimodularity condition of the R matrix. And also, it turns out you can take a twist that is strongly cyclic, and you can turn it into a twist that is weakly cyclic. But what you cannot do is to take a twist that is weakly cyclic and turn it into a twist that is not weakly cyclic. So this is literally a property of the equivalence class of twists that you can consider, and not just of one particular twist.
Okay, because I'm thinking, for instance, of like an example like with the kappa Poincaré kind of quantum algebra, in which you have some star products that are like manifestly non-cyclic. And then, I mean, I don't know, maybe you can do something like modifying the trace of the integral or something like this to appear like more cyclic. But I might be wrong. So, but I remember that there are some instances in which like sort of when you choose the ordering for your like non-commutative planar exponents, you find some manifestly non-cyclic.
So I mean, Kappa-Minkowski is special in that sense that for most of the theories, like when you are just talking about, well, you can have various twists that lead to Kappa-Minkowski space. But well, in principle, most of them we cannot tackle with this approach, because either it's not given, like the twist is not constructed via symmetries of the undeformed model, or it violates the weak cyclicity condition. And we just make no statement about those. Like when they don't satisfy our conditions to start with, we cannot deal with them in this picture. That's it.
Okay, so essentially you're starting from like, you know, classical non-modified Yang-Buster equation where the R matrix gives like some abelian twist. And, okay.
Well, not just abelian, but well,
well behaved kind of. Okay.
So one caveat even there, like when you have supersymmetric versions of field theories and you impose a Kappa-Minkowski twist, there's this Jordanian thing, you can unimodularly extend it maybe, and then there's some possibilities that you can deal with them in the way that we deal with them as well.
Okay, thank you.
So suppose that you have a deformation of a non-relativistic limit of the n equal 4 super Yang-Mills, the Galilean Yang-Mills. How much of this construction could be applied? Or in other words, how much do you rely on Lorentz invariance?
It's a good question. I can just, well, I mean, the thing is you want to have, I mean, we really need to have symmetries of the undeformed theory under everything that appears in the twist. So with this construction is something that we have to deal with. But in principle, what I could imagine what could be possible is to do this deformation and then take some limit to some non-relativistic objects, and then maybe that works. I have no experience with that.
Hi, do you know anything about the number of non-equivalent twists under fields redefinitions?
The number?
Yeah, as in how many can you create for a theory, or like what is a classification or anything like that?
I mean, various kinds. Like, so you even have like different algebraic, already different algebraic classes of twists. So you can have abelian twists. So the examples that I showed to you were all abelians, where all the generators that appear in the twist, they commute with each other. You can also extend them to non-abelian classes, and there are also these Jordanian twists that also have been talked about earlier the week. And yeah, so but about the number, I don't know.
Right. So sorry, just to make sure I understand. So you did not address the actual question. You just said there is like various classes of deformations.
I mean, to be fair, like these twists, they are like the R matrices and the twists, they are classified. So you can, like, especially for PSU 2,2/4, you can see them, like it's understood. I just don't know from the top of my head.
Okay, cool. Nice, thanks.
I'm Hayden, thanks for the talk. Does your active picture help in constructing Seiberg-Witten maps, for instance? Because if I remember, those are kind of open problem for most of these twists, except the dipole ones.
Exactly. Like in dipole cases, it's quite easy to, in principle, you just dress your fields with Wilson lines, and then you get from the picture of non-commutative gauge theories to their, well, ordinary gauge theories, equivalence kind of with this Seiberg-Witten map. But in general, that's not the case. And I also think that our approach cannot really help to understand this, because we are not changing the basic properties of the twist itself. We are just changing the picture so that we can write down the theory in a better way, in principle.
And you don't need this Seiberg-Witten map for anything in your construction? I'm always a bit confused. What should be the role?
So
in this?
For constructing the theory, you don't need the Seiberg-Witten map. The Seiberg-Witten map might appear when you want to look at gauge invariant operators and how to construct them, because in principle, it should be easier to construct them in one or the other picture. But this is basically, these are the next steps, kind of.
Yeah. Okay, thanks.
Okay, I just want to clarify about the planar equivalence statement. So what the actual statement is that if you have a non-planar Feynman diagram, then you cannot remove the stars from the internal lines. And what's the requirement to be able to remove them from planar ones? Is it just it should be a standard Drinfeld twist? Or,
well,
should it be a billion also? Or
no, it's like, in principle, what you need is you have to have a star product that is associative. It has to be cyclic under integration, and like the deformation of the propagators have to be linked in some way to the deformations of the vertices. And this is exactly the case that we have for all these kind of models where we have the weak cyclicity condition for a twist. If you can construct a star product that is not built from a twist but somehow satisfies all these conditions, it might work as well. I don't know if such an object exists, like, but for every kind of Drinfeld twist that meets these two conditions, like the planar equivalence is completely fine.
Okay, there is also an online question. So, and I think the online person can just ask its question, or?
Let's see, can you hear me like this?
Yes, we hear you.
Yes,
Perfect.
okay, that's great. Okay, Tim, thanks for a nice talk. I just wanted to ask something.
Maybe wait a second, Stein, because we hear you several times. So
okay. Is it changing now? Is it better?
Just yeah, I don't know.
Or should I type my question?
When you speak very, very faint, perhaps it gets better. You can speak loud. Try it again, Stein.
Okay. Can you hear me well now?
Yes, we can.
Yes, okay. So the question you maybe are expecting, in a sense, since you mentioned it so explicitly about supersymmetry and so on, I was always a bit confused, and I still am a bit confused about what you would do if you work in component fields for gauge theory, for supersymmetric gauge theory, because there's like these gauge transformation terms that appear in your symmetry transformation. So how would you deal with them in your active symmetry transformation picture, since you're saying you can cover them?
So yeah, I mean, the way how we can cover them is in principle, when you work in the right language, you take your undeformed theory and, for example, you can package it in superfield formalism, and then you have a notion, or you have a formulation, like even before taking things like West-Zumino gauge. There you have exactly these requirements that we have.
Sure.
So in principle, what you could do is you could write down a theory that has all these horrible auxiliary fields, and you can even integrate out the Grassmann variables, so that's also fine, and then directly impose these supersymmetry transformations on all the fields that you get. What's definitely true that when you directly work in the picture where you just have the physical fields in n equals 4 super Yang-Mills, then you have terms that transform with covariant derivatives and so on. And for those, in principle, they don't meet the requirements for our construction directly.
Okay, so you're saying you would need to work with all these auxiliary fields, or not even just auxiliary, all the gauge, like the gauge fields that are there, but not gauge like the spurious gauge fields or whatever that you want to.
That's in principle what might happen, yeah.
Okay.
I mean, you might be able to simplify afterwards and get something, but this is something for the future. Like so far, we just construct these things, and we have a way to kind of deal with this in some way.
Okay. Cool. Thanks.
Okay. When we look at the time, I think we should stop it here. But of course, I think Tim is still around a little bit, so you can also ask him further questions during the break. Thanks again for this very nice talk. And of course, also thanks again to you for this nice discussion which we had.